Hello YouTube, my name is Dr. Paul Kerstetter. Today I would like to talk about deserialization in FPGAs. Deserialization is defined as converting a serial bit stream into a parallel bit stream. An application where this might be useful is an analog to digital converter interfaced to an FPGA. Deserialization in FPGAs using ISERDESE2. The ISERDESE2 is a deserializer primitive available in all Xilinx 7 series devices. It's similar to the ISERDESE3 found in ultra-scale FPGAs, but interestingly, the ISERDESE2 actually offers more features. That's right, in ultra-scale they simplified the block and reduced the feature set. So, what does a deserializer do? It takes serial data and converts it into parallel data. For example, in the diagram, the serial data is shifted into an 8-bit shift register and then captured by an 8-bit register using a divide by 8 clock. But why would we want to do that? The short answer is to make timing closure possible. The ISERDESE2 deserializer is special in that it operates at a higher speed than what the rest of the Arctic 7 FPGA can handle. For example, one common case is when an ADC or analog to digital converter interfaces with an FPGA. Modern ADCs have moved away from parallel interfaces and towards serial ones. Why the change? Parallel interfaces require every single line to be exactly the same length. As sampling speeds rise, even teeny mismatches cause timing errors. Achieving perfect trace matching becomes nearly impossible. Serial interfaces solve this problem. There's only one data line to match. Sometimes the clock and data even share the same line. But there's a trade-off. All that data has to move through a single wire, so the data rate skyrockets. An ADC might output 1 gigabits per second digital data if it is using DDR or double data rate. Data is captured on both the rising and falling edges, meaning the clock only needs to be 500 megahertz. Here's the challenge. An Arctic 7 FPGA can typically handle up to 400 megahertz on a single data rate line. That's where the ISERDESE2 comes in. It can handle serial data rates up to 1.25 gigabits per second, letting you easily meet the timing of 1 gigabits per second stream. The ISERDESE2 is a dedicated serial to parallel converter with built-in clocking and logic features for high-speed source synchronous designs. It eliminates the complex timing issues you'd face if you tried to build your own deserializer in the FPGA fabric. Its key features include dedicated high-speed deserializer, SDR and DDR modes, supports 2 to 8-bit parallel outputs in SDR and 4 to 14-bit bits in DDR, works seamlessly with source synchronous interfaces. You can find more technical details in the AMD documentation shown in the link. Unfortunately, the AMD documentation doesn't provide the timing details needed to reliably bring up the deserializer. But don't worry, I've worked through those issues and I'll walk you through them. The serial clock, divided clock, and data rising edge must be aligned in time. If your simulation shows red X's outside of reset, that usually is a sign that the divided clock isn't aligned correctly with the incoming data. Also note the deserializer expects the LSB first on the serial stream. Finally, if your incoming serial clock is differential, you'll need to buffer it properly. Use a differential buffer, for example, BuffIO or iBuffDS, for the serial clock path, and a single-ended buffer, for example, BuffR, to generate the divided clock. I have a working design and timing simulation linked below in the description so you can follow along. Let's switch over to the video where I'll show you the timing waveforms and explain how the clocks and data are handled together into the deserializer. So this is the Vivado project, and in design sources I have the VHDL code. And that VHDL code is here. Let's maximize this window. Here's the entity. You can see that I have a clock, serial clock going in, a complement of the serial clock, a divided clock, the serial data going in, a reset, and the parallel data going out, which is Q. And this is the primitive, the ISERDESE2 primitive instantiation. Here we have it set up for double data rate. It can be set up for single data rate if you want. The data width is 8 bits. It's set up for networking. It says networking for simple serial to parallel conversions. An alternative would be for like DDR memory. But this is set to networking. You can use this with a delay primitive, but I have no delay primitive, so I have that set to none. This is the parallel data from 0 to 7. That's 8 bits of parallel data going into the queues. Here's the serial clock. It's actually a 500 megahertz clock. And the divided clock is 125 megahertz. The serial clock as a complement, clock B, which is the inverted 500 megahertz clock. Data in is the serial input. This Serdes, the ISERDE2 primitive actually has a bit slip capability where it barrel shifts the bits and that is used for bit alignment. But in this case, I'm not using bit slip. It has a reset. I'm not using the I delay. A bunch of unused ports. You can use these ports to attach a slave ISERDES2, but we're not doing that in this case. And here we have the conversion or the parallel output assignment. Okay, back to the sources, and then in the sources we have the simulation sources, and there's a test bench in here. And we'll maximize the test bench. And the main thing about the test bench is the clock period, which is 2 nanoseconds, which is a 500 megahertz serial clock. The divided clock is 8 nanoseconds, which is 125 megahertz clock. The ratio is 4, and the reason why the ratio is 4 is because it's double data rate. So you have 8 serial bits in, and then you get 8 parallel bits from that. But because it's double data rate, the divisor ratio is 4. And this is actually where the data is that I'll be sending. Okay, so there's a clock generation process for the serial clock, a divided clock process for the divide by 4 clock. Then we have the data process. One of the important things is to get the, if you want to see bit alignment in the simulation, then you have to adjust this wait for statement in order to time when the data comes out relative to the divided clock and the serial clock. So I have wait for 15 nanoseconds. Anyway, this process shifts out on the serial line the data, and the data is A5, 3C, F0, 5A. And then there's a reset process. So let's run the simulation. You go over here, click on that, run behavioral simulation. Okay, expand the window. Let's expand the waveforms. So one thing I want to show you, I want to talk about the timing of the signals. If you look here, we have the data, the parallel data A5, 3C, F0, 5A. And if we put the cursor on the rising edge of the divide clock, the divided by 4 clock, you can see that that's when the data changes or is registered. And that's A5 is registered. And the next time it changes is on the next rising edge of the divided by 4 clock. And as you can see, that's when the data is changing in the parallel register. Now, the question is the serial data, when exactly does it start reading the serial data? You can actually shift the serial data relative to this reset. It comes out of reset right here. And you can shift this data and you will get bit alignment eventually once you get it in the right position, and that will give you the correct sequence here for your parallel data. But when exactly does it start reading these bits? The first data, remember the serial data comes out the least significant bit first, and our lowest order bits in our parallel data is a 5, and coming out least significant bit first, we would then expect the serial stream to be 1010, and that's what we have here, 1010. And if you notice, it occurs, the reading of the data occurs on that rising edge of that clock, the serial stream clock, which is on the falling edge of the divided by clock, and so that's when that registers that first 1 in the serial shift register. And so that's really kind of the key, is to look at the falling edge of the divided by 4 clock, and then look at and the data that will be clocked into the first 8 bits of the parallel register A5 will be the serial data that is from the falling edge of the divide by 4 clock and the falling edge of the divide by 4 clock, the next falling edge of the divide by 4 clock. And so that's how that timing is. And so 1010, and then we would get the A pattern, which is 0101. So then you would get, 101 for the 5, 0101 for the A. And if you notice that those bits, the A5 or the 5A is within the bin of the falling edge of the divide by 4 clock and the next falling edge of the divide by 4 clock, those bits right there. So that's how that timing occurs. And I just wanted to point out one more time, you have the rising edge of the serial stream clock aligned with the rising edge of the divide by 4 clock, aligned with an edge of the data, the serial stream data coming in, and that's how that's supposed to be timed. But let's say that, for example, that your divided clock is the complement of what I'm showing here. And to do that, I can go back here into the test bench, and I can do the divided clock and change it to a 1. And I can do the divided clock and invert it by changing that to a 1 and that to a 0. And if we run that simulation, I'll show you what we get. Okay, expand the simulation window, full screen, and oops. As you can see, we're getting more red now. We're getting collisions when the data is present on the serial line. This is not good, and the reason that is because the divided by clock is shifted, is inverted. So it got inverted, but what's interesting is we still have the right timing relationship. We have the rising edge is of the streaming clock is in line with the divided by clock and is in line with an edge of the data, but here we are getting collisions, and so that's really deceptive. That's really deceptive. How do you know if it's right? And it must have to do with when in the relationship between coming out of reset and here we show we're coming out of reset on the rising edge of that clock, the streaming clock. But all I changed was a divided by clock, and I inverted it. And what that did is it made this into a collision, which you do not want this. This will cause you problems. So we'll change it back. And you notice here, reset is coming out of reset. It's right in the middle of a divided by clock, and it's in line with a rising edge of the streaming clock. So it's probably not the best place to have you come out of reset. The reset should be, you should be coming out of reset like in between the falling edge and the rising edge of the clock. So, but let me switch it back. And you will see that the collisions go away. So there's 3 places to change that. Rerun the simulation. Okay, let's expand the window. Now you see we don't have hardly any collisions anymore down there in the parallel data. And so reset is coming out in between 2 edges of the divided clock. So be on the lookout for that. If you're having problems with collisions, you might want to try retiming your divided by clock. Okay, so the final thing I want to show you is the clock buffers. And I have the clock buffers in a different design, so I'll have to open that. In this design, the VHDL, the top level VHDL code is called RTD. I'm going to open that. And so this is the top level for that. But there's a bunch of stuff in here which isn't important, and I'm not going to share this. However, what I did want to show you is, okay, what I want to show you is it's the clock coming in for the ADC is a DCO clock, DCOP and DCON. That's the echo clock for the ADC, and that comes in the iBuffDS buffer as a differential LVDS signal, and it outputs a single-ended signal, DCO int. And then that goes into our, that is used to generate our divided down clock. In this case, instead of 4, like my previous example of a division, it's a divide by 3 clock. And so the input to that is the single-ended clock, the single-ended serial clock, and the output is the divide down by clock. And that is divided by 3. So we use the buffer, the BUFR, to do that. And so that way, your serial clock input, you have your divided clock, and you have your data input, your serial data input. And so if you do that, then you will be able to meet timing. And so that's all I wanted to show you. I hope you enjoyed this video. If you did, like and subscribe it. And I'll see you in the next video.